Hey there, creative coders! This is Benjamin D. Whiting, and welcome back to the Super Collider segment of Null-state's interactive digital art tutorial series. Last week we discussed using trigger math to achieve conditional-like functionality in server-side programming. This week we'll introduce the protocol that ties Super Collider together, Open Sound Control. We'll also dive into using OSC responder functions to allow the server to send information back to the client. Let's get started. Before we dive into using OSC responders to bridge server and client-side programming, it's important to understand just what OSC is. OSC is an abbreviation standing for Open Sound Control. Open Sound Control is a protocol developed at UC Berkeley's CNMAT by Adrian Freed and Matt Wright, used to network audio software and hardware together. It is often seen as a competitor to MIDI. Indeed, OSC brings with it several distinct advantages over the aging 1980s interface, though they are not at all mutually exclusive. It is not uncommon to mix OSC and MIDI depending on one's use case. While one can visit the Open Sound Control website at opensoundcontrol.org to get in-depth information on the protocol, along with a fuller grasp of its potential, for our purposes it's enough to understand what kinds of data it can send and how messages should be formatted. OSC can send integers, floats, strings, and what are called blobs, basically arbitrary binary data that could be a fragment of PCM audio, video, anything really. OSC messages begin with an address pattern resembling that of a URL or Unix-like file system path, followed by a type tag string so the receiver will know the type or types of data being received, and OSC arguments, i.e. the data. Super Collider helpfully handles the type tag string for you, though it is important to be aware of it should you wish to ship OSC messages out to another application. More important to master is the address pattern. Those who have used terminal emulators in Linux and Mac OS will feel right at home, but for those who haven't, it follows this syntax. The only required bit is the path, preceded by a /. Subpaths are optional, but this kind of structural hierarchy is a large part of why OSC is so useful for interfacing with other languages and/or control hardware. For instance, you might want Super Collider to respond to OSC messages from a controller with several buttons and knobs. While one could give each component its own path, it's much handier in the long run to give each type of control a path and then an individual component a subpath, like so. This is especially helpful when wanting to listen to or sending data out to an entire family of components at once. For those of you already familiar with MIDI, you may be pleased to discover that OSC accommodates 32-bit integers and floats. Compared to MIDI's 7 and 14-bit integer limitation, OSC offers a much greater degree of resolution. Again, it should be stated that one need not choose OSC to the exclusion of MIDI. OSC and MIDI can coexist happily in Super Collider, which is helpful as MIDI-capable devices are still overwhelmingly more common than OSC-capable devices. I've stated multiple times in this tutorial series that sclong communicates with scsynth via machine language and OSC messages. However, what I have yet to mention is how sclong itself can be set up to listen for OSC messages, originating either from itself, scsynth, or some other source. This is accomplished by using an OSC responder function. OSC responder functions come in two flavors, OSCFunc and its subclass OSCdef. Notice the capital F in func, yet the lowercase d in def. Both classes are virtually identical in how they behave, though OSCdef provides some tasty extra features as it stores the def's symbolic name in a global dictionary, thus enabling it to respond to global OSCdef exclusive class methods like .freeAll. However, depending on one's use case, these globally targeting class methods may not be particularly useful or relevant. In that case, OSCFunc may be more appealing to use as there is often less text to type, OSCFuncs can quite neatly be embedded within other functions, and OSCFuncs can be used in Super Collider class files while OSCdefs cannot. Even though OSCFuncs are not recorded in a global dictionary, Invoking instance methods on individual OSC funcs after instantiation is possible via environmental variables. In fact, it can be a little more convenient, as ~defname.method requires fewer keystrokes to type than OSCdef open parentheses \defname close parentheses .method. A word of caution. Before the release of SuperCollider version 3.5, OSC responder functions were handled by a different family of classes. The appropriately named OSC responder and its subclasses OSC path responder, OSC responder node, and OSC multi-responder. These classes are not as robust as the newer OSCFunc and OSCdef classes, as OSC data sent along the same paths can conflict and overwrite each other if one is not careful. Furthermore, they are more confusing to use, as argument order is not particularly intuitive, and they do not support nifty features like pattern matching or custom receive ports. However, they have stuck around for years, as a ton of older tutorials and SuperCollider plugins use them, and the inevitable breaking of compatibility has made many reluctant to pull the plug on including these classes in contemporary releases of the language. That said, they were scheduled for removal from the current version of SuperCollider, 3.10, and while the decision was eventually rescinded before the public release, I'd say the prospects for the inclusion of OSC Responder and its ilk in 3.11 are not looking too good. If you run across older code that makes use of them while learning the language, convert them to OSC funcs or OSCdefs before using them in your own programs. I may include a bonus video walking one through such a conversion later on down the road. Here is the syntax for OSCFunc. Like with most classes, specifying the .new instance method is optional. There are other arguments after path, but they're meant for certain kinds of circumstances that are not relevant to this tutorial series. Similarly, OSCdef takes on the following form. As implied by the name, an OSC responder function responds to incoming OSC messages. As long as no message is being received, nothing happens. Once the responder detects an incoming OSC formatted message, it passes its contents, packed into an array, into the function, along with a timestamp, an IP address from which the signal is detected, and the port number over which the message is being received. The function is then evaluated. In fact, the final three arguments are seldom used, though they can be useful to filter out undesired input. I myself have made use of the time argument to debounce chattery Arduino input. Therefore, with all uncommon arguments stripped from the class, a typical OSCFunc template looks a bit more like this, where an OSCFunc passes the contents of an OSC message, received over the stated path, into the enclosed function. Much cleaner, no? This is because unnecessary arguments do not have to be declared. Even though sclong will pass the other information into the function, without argument declarations, that data has nowhere to go and will be summarily ignored. Let's now concoct a quick synth-OSC responder function pair to demonstrate how all of this works. We'll use the full argument list in the OSC responders function so you can see exactly what is being sent. Even though we're not going to be outputting any sound, we'll still need the server as we'll be using an LFO, so let's go ahead and boot it first. Now on to our code. In this function, we'll have a non-interpolating low-frequency noise generator generate a random value between 0 and 1 once a second. Wait, what's the SendTrig class? Well, as a server does not typically talk to the client via OSC, we need something that will instruct it to do so. There are two classes that accomplish this, SendTrig and SendReply. SendTrig is the easiest to use, though as its name implies, it is meant to send simple trigger info outward and thus is fairly limited. SendReply is far more useful, but we'll get to that later. For now, SendTrig suits our purposes just fine. The first argument in SendTrig is the trigger. Let's use a control rate impulse UGen pulsing at a rate of once per second. The second argument is the trigger ID, which is unnecessary in our case as we're not sending out multiple triggers. The final argument is the value we're including in our OSC message. Let's send out the state of our LFNoise UGen every time the impulse pulses. Next, we create our OSCFunc. Typically, one would want to assign it to an environmental variable so it can be released when no longer needed. But for our purposes, such a measure is unnecessary. Come to think of it, We didn't even really need to set our synth to a variable either, as no sound is actually being bused to our speakers. We're just going to use command period to free it anyway. We pass all pertinent info into the function, which is then packed into an array and printed to the post window. It will do so every time an OSC message is detected along the path /tr, which is the path SendTrig is hard-coded to output to. Let's now execute this code block and see what happens. Okay, so that's quite a lot of information posting every second. But again, a lot of it can be filtered out in your own OSC funcs, as it's really superfluous data. The first index in the posted array is the message content being sent out via SendTrig, itself packed into an array. The first index here is the path, which is always /tr if you're using SendTrig. The second index is the node ID of the synth, useful if more than one synth is using SendTrig to output triggers. The third index is the trigger ID as specified in SendTrig. Again, useful if more than one SendTrig is used in one synth, or as an alternative to filtering via node IDs. The fourth slot, or index 3, is the creamy nougat at the center of our message, the value being sent from our synth. Moving back to our OSCFunc generated array, the second index is a timestamp in seconds, counting up from when the server was booted. The third index is the IP address and port of the message sender. Unless expecting data from a remote machine, it will be the loopback IP address along with 57,110, the latter being the port that the server listens on and sends from. Finally, we have the receiving port, which will always be 57,120, the client's port, unless specified otherwise in our code. Command period will terminate both the synth and the OSCFunc. Yes, command period will end all OSC responder functions, be they OSCFuncs or OSCdefs, unless set otherwise. One can make an OSCFunc permanent by using the permanent instance method and setting it to true, like so. However, should you decide to do this, then it is a very good idea to set the OSCFunc to an environmental variable, as otherwise there will be no way to release it without rebooting sclong. Now let's adapt this code so that the trigger is tripped only when the LF noise generator outputs a value above 0.7. Let's also rework the OSCFunc so that unwanted arguments are filtered out, and we're only outputting the random number being received in the post window. We'll include a string to the random number, packaged in index 3 of the message, to better contextualize what is being posted. Now, when we execute this synth OSCFunc combo, we should see a new posting every time a random number greater than 0.7 is received. While I had referred to the client versus server-side programming mini-series as a tetralogy last episode, I must confess that it will be a tetralogy in the sense that The Hitchhiker's Guide to the Galaxy is a trilogy. It turns out the original script for this episode pushed us past the half-hour mark. As we're trying to keep these episodes down to easier to swallow 10 to 20-minute bites, this episode will be split in twain. Next week, we'll continue right where we left off, using an OSC responder function to spawn synths via a combination of random number generation and mouse manipulation. We'll also work with clonk and clong, two very useful unit generators that allow for the easy generation of more complex sonic material than we've been working with up to this point. In the meantime, please don't forget to hit that like button and subscribe to this channel to show your support for more interactive digital music and art content from us at Null-state. Also, make sure to check out our Facebook page and webpage to stay up to date on all of our upcoming events, workshops, and concerts. The link is in the description below. See you next time!